Hi, today we will talk about the speed control techniques for induction machines. Just as a reminder, let's talk about the operating modes of induction machines. As you know, if it is operating as a motor, then the slip is like between 0 speed and less than the synchronous speed. So the slip is between 1 and 0. So if you are, write it here. So if you are in this range, okay, so that means you are operating in the motoring region. However, if the MMF and the rotor position is moving in the opposite direction, so that is the rotor speed is negative with respect to MMF, so in that case our slip is actually larger than 1, so it is called plugging or braking region. Again, that is not really efficient way to drive a machine, and it's not used, except for emergencies and for rare applications. And other case, again, all electrical machines can operate as a motor and a generator. And for generating mode, you have to run faster than the synchronous speed, so you need to exceed the synchronous speed of the stator excitation. So in this case, as you are getting faster, so in this range, so slip is actually negative, so slip is less than 0. So that means in that case the machine is converting mechanical energy to electrical energy. And again, just to review, let's talk about the power flow directions in those operating modes. In the motoring mode, so you apply some input power in the electrical form, and it is what 3 V phase I phase times cosine theta. The real power is different from the apparent power, and there's some power factor issue. But if you take the real power input to the motor, then you have a couple of loss components. The first one is the stator copper loss or the stator core losses. Then after that, remember, in the equivalent circuit, then we are going from the stator side to the rotor side, and that transferred power is called the air gap power. Then in the rotor side, we have the rotor copper losses and other extra electrical losses like the currents in the end rings, etc. Then we have in the equivalent circuit, then we have the mechanical power, which is the power, remember, in the power dissipated in the equivalent circuit in the R2 prime times 1 minus S1 minus S over S. Okay, so then you have the mechanical output power. Then through that one, then you will have the mechanical losses. Then you have the shaft power, which can be transferred to the load. Okay, so if you come to the generating side, then the power direction is reversed. So now we are converting mechanical energy. So our input power is the mechanical energy, but those are not added. So it's still, you supply some mechanical power, then you still lose some of them in the friction. You still lose some of it with the copper losses, etc. Then you have the air gap power. Then you have the iron and copper losses in the stator. Then you will have the output power. Okay, so you need to remember those things are always lossy components. So there's not a way to make your efficiency more than 100%. In the plugging mode, so again, it is kind of different because it's not really in the generating mode, but you are still consuming some power. You are still consuming some power from the power supply. So actually, you are using some electrical power. So that power is transferred to the rotor, and your mechanical. If I go back, so you were here. So you are still getting some torque from the mechanical side, and both of those things will be dissipated as heat in the rotor. So again, that braking or plugging mode is not used for continuous operation that will easily damage the electrical machine. But for example, if you want to quickly stop the machine, then you can apply that kind of operation. And some people ask like how we can make it into the plugging mode. But again, if you want to, for example, if you have a crane and if you want to go up and then the rotor goes down, so that is a plugging mode of operation. Another way is, instead of changing the direction of the rotor, okay, so you can change the direction of the stator MMF, and that can be done by replacing any two terminals, interchanging any two terminals. So instead of, let's say, MMF rotating in the counterclockwise direction, you can make it in the clockwise direction. And actually this changing these two terminals is, the easiest way of an induction machine, or actually for synchronous machines as well, to rotate in the opposite direction. Okay, so, and when we put all these together, okay, at the end of the day, I want to talk about on the system level. So we are applying some voltage, and our motor produces some torque. So that torque is our electrical torque, and in this equation I didn't show the friction forces, but you can add those things into the load if you wish. Anyway, so we produce some electrical torque, then our load, whatever it is connected, I don't know, it can be an electric car, it can be a fan, it can be an elevator, crane, robotic arm, what you call it. So it has its own load torque, okay? So the difference between these two, if you produce more torque than the load torque, then that means you have extra net torque in the system, and it is the same as like writing F is equal MA, or let me write it, F is equal to M dV over dt. So if you supply some net force, then your system, in linear systems, it will get accelerated, and rotational systems, its rotational speed will increase. Okay, so whenever you have equal torque, okay, equal electrical and load torque, that means the omega over dt will be 0, so the system will operate at steady state conditions. So whenever there is no difference between the electrical torque and the load torque, so the system will operate at the steady state. So those defines the intersection points between the motor torque line and the torque line. For example, let's have a look at that curve. So T load 2, I think it seems like a fan load. So the torque of the load increases with speed. If you want to rotate a fan faster, then it will create more torque. So if your machine is producing that kind of torque characteristics, if you just start the machine from here, so your electrical torque is larger than your load torque, okay? So when you do that subtraction, you will have a positive value. So that means your speed is going to increase. So then it increases its speed. So it comes to here, right? Then you make it again. So it just still keeps accelerating. So basically you are using that excess torque to increase the kinetic energy of that rotational system. So you are storing that power, that energy in the 1 over 2 j omega square torque. Anyway, so it just at that point you create more torque, then it just, the torque of the machine starts reducing, but it is still, positive until you come to here. So at that point, actually T electrical is equal T load. So that means d omega over dt will be 0. So you will be operating here. Okay, so then let's say your load is changed to the second line, maybe it increased and that kind of thing. So now you have that intersection point. So what's happening there is now your torque, okay, you are operating here, but then at that point you are in the negative range. So from going from C to B, okay, let me write here, from C to B, basically T load is larger than T electrical, okay, so therefore d omega over dt is less than 0, so it will reduce its speed, okay, it will reduce its speed until where? Until they meet in the balance position, and once they have at B, okay, at point B, again T load is equal to T electrical. Okay, so graphically, the operating point, steady state operating point shows us the intersection point shows us the steady state operating point, but that doesn't mean, okay, that's a common mistake, that doesn't mean you can just go from point C to point B instantly, okay. Don't forget, in any mechanical system you cannot change the speed instantly, because changing the speed instantly means having a step change here, and since it has an inertia there, so having a step change in the speed implies you need to have infinite torque, which is not possible. So it always takes some time to accelerate or decelerate system, and what happens during that time, either your machine is operating as a generator or running as a motor, but the power flow changes, the amount of current it draws changes. Another interesting point is point A, okay, point A. What happens, for example, let me clear that part a little bit. Okay. So mathematically, so this is the motor torque characteristics and this is the load characteristics. So you can say there are two, points that our motor can run at steady state conditions. Yes, mathematically it is correct. If you solve those equations, you will find two solutions. But in a practical case, the motor will, never run on point A. Why? Because that one is called unstable. This one, point B and C, are called stable intersection points, and that one is called unstable point. Why? For example, if you are here, okay, if you are at point B, and somehow, due to friction and other disturbances, maybe in the voltage current, maybe the machine generates some kind of torque with harmonics, whatever, so it will not be perfectly ideal constant voltage. There will be always some slight changes. If you somehow, your torque or load generates somehow like slightly larger torque, or let's say if your speed suddenly reduces, if that one is, I don't know, 1000 rpm, if your speed suddenly drops to 999.999, okay, so that means your torque is still increasing. Let me draw that one, point B. So if you have here, so this is your point B. If you go there by delta X, then you will have more torque. So at that point, the system tries to increase its speed. And somehow, if you just move at that direction, okay, and I'm talking about like really small changes here. So at that point, so you will have now negative torque, so tries to reduce speed. So it is like a, those things here, sorry. So it is a feedback mechanism, okay. However, let's have a look at point A here, okay. So if we look at point A, let me draw it again. So it is, in this case, of that kind of graph, point A. Again, if you somehow move by delta X, so now your motor produces more torque, so increases its speed. Okay, and somehow if you just move along that direction, so now your motor generates less torque. So from that point it tries to go that way, so reduces speed. Okay, so this is, it has like a feedback mechanism. So this one has like feedback, but that one has feed forward mechanism. Okay, so mathematically you can have two operations, but once you are in point B, the machine will keep running at point B. However, if you are at point A, so it is really difficult to maintain its speed. Either it will go that way or that way until it reaches another balance point or until it stops. Okay, so actually that can be, I have my pen here, and actually I have two balance conditions for my pen, right? So if I just keep my pen like that, so it is at point B, I can give some disturbance, but it will still keep at point B. So point A is a balance point like that. Okay, technically it is possible, but if there's any slight disturbance, so it will get away from that point. So just, you know, be careful about using, you know, blindly mathematics, because if you solve the equations, you can find point A can be possible, but from an engineering point of view, it will not run at point A in under stable conditions. Okay, so I can have different speed control problems, and I can have the load constant and speed reference is variable is changing, so you want to accelerate your motor under load constant load conditions. Maybe you want to keep the speed constant, but you have some disturbance at the load torque, and that is, you know, varying. Or, you know, you can have both speed reference and load is variable. Although there are some open loop control systems, it is really common to have some closed loop motor control systems, and actually you are seeing that kind of problems in your control theory classes. And actually we need to modify machine characteristics, or, you know, supply characteristics. Here you see a system representation. So at the end of the day, I have my voltage source. Okay, I can control how much voltage is applying, or as we discussed last week, maybe I can control extra resistances and that kind of equipments. So it produces some torque, and I have my mechanical system, and from mechanical system I have my speed, and from the speed, again, if you take the integral of the speed, you can have the position. So if you just implement a control system, it is something like that. You can have a power source, then you have a converter, power electronics controllers, and actually we will discuss those things in the fourth year. Then you have your motor system, and then if you need to do some, let's say, closed loop position control, I don't know, for a robotic arm, for example, a robotic arm would like to go to one place, take an item and put it there, or an electric car or an elevator, for example, you want to go to the 5th floor. So there are some kind of sensors, position sensors and speed sensors, and you have some either reference in the position, or you have some speed command, and then it just compares it with the actual position and speeds. Then you have the speed controller. So these are, you know, PI controllers, so you can actually calculate how much current should I give to the motor to produce the required torque. Then the current controller calculates, in order to give that amount of current, what voltage should I apply to the motor. Then the voltage command is sent to the power electronics or that kind of controller. So, and actually you can measure those things, and actually you can have some current sensors in the system. And again, as you see in control theory classes, it is possible to get a transfer function both for the mechanical system, electrical motor, etc., and you can design the best controller. So actually, while applying that converter, or what will be the input of our motor, depends on the type of control or the requirements of the system. And one of the simplest control is variable voltage control, and actually we use the same technique to start up the motor or to limit the starting currents in an induction motor. So we know electrical torque is proportional with the square of the voltage. Okay, so if I just reduce the voltage to half, the peak value of the torque and all characteristics will be reduced to 25% of the actual value by halving the voltage. But the interesting thing is the synchronous speed is constant, because in that type of control we are not changing the applied frequency. If we are applying 50 Hz, we are still applying 50 Hz. So our synchronous speed is constant. So as that one is not changing, if you want to make a speed control using voltage, for example here, if you have like a low torque like that, so initially you can operate here and you can reduce the voltage to, let's say, 1 divided by square root 2, then you will have a speed control during that range. Okay, or if you halve the voltage, then you will have a speed control range. Okay, this one, so you will have a narrow control range. Okay, again, technically, you can maybe reduce the voltage even more, but then the torque is reducing with the square, and probably you will not generate enough torque to even get over the friction, or like the minimum torque required by the system. Okay, so then other option is to use rotor resistance control, and again we talk that one as a method to reduce the starting currents in an induction motor. We have the same problem here. The synchronous speed is constant, and actually if you increase the rotor resistance, and that one is only applicable to wound rotor induction machines. In squirrel cage induction machines, you don't have those terminals to connect the external resistance in the first place, so it is not it's not applicable to squirrel cage induction machines. But however, if you increase that rotor resistance, your torque curve moves in that direction. So again, for speed control, maybe you have that kind of range. Okay, but it is really useful in some applications where you need a high starting torque. For example, in mining, they use some electric motors to crush the rocks into small pieces, and those mechanisms require really large starting torques at low speeds. Okay, so initially you have your starting torque here, but by increasing the rotor resistance, you can have increased starting torque. So again, that can be useful in some applications if you want to start the machine really quickly, or if you require to operate at lower speeds with high torques. Okay. Again, for speed control, again, it is not really flexible. So what I can do is I can, for example, change, like similar to changing the magnitude of the voltage. So that's what we did here. So instead of just changing the voltage magnitude, what happens if I change the frequency of my voltage? Okay, so let's have a look at those things. So if I change my frequency, okay, so I can move my synchronous speed as increase or decrease, and actually I can change my slip, and as the slip changes, the torque changes, and I can control my machine to go faster or go slower. So here there are a couple of examples. So for example, initially, so this is increasing speed, okay. So here, this is your load torque, and initially you are operating at that point, and I want to go from this place to that place. So for example, I want to increase my rotational speed from 900 RPM to 1000 RPM. Okay, so what I do is, while the machine is running here, and at that point, let's say the black line has a synchronous speed of, I don't know, 1000 RPM synchronous speed, and the machine is running at 900 RPM. So I suddenly increase my rotational frequency, okay, from, I don't know, I couldn't calculate, but from 50 Hertz to 60 Hertz, for example. Okay, so once I increase my frequency from 50 Hertz to 60 Hertz, now my synchronous speed is not like 1000 RPM anymore, but it is 1200 RPM, the synchronous speed. So as the synchronous speed changes, again, you cannot make a initial jump from that speed to that speed, okay? The speed cannot change instantly. So what happens is you can change the applied frequency. So suddenly now the machine characteristics are at the blue line, and I am still running at the same speed. So now my operation, not steady state operation, but the new operation point, once I increase the frequency to 60 Hertz, jumps to here. Okay, so now I'm still running at 900 RPM. Okay, but instead of let me write it here. So for example, initially NR synchronous speed was 1000 RPM. So NR was 900 RPM. This is 50 Hertz. Right? So then I increase it to 60 Hertz. So NS becomes 1200 RPM. And it is at like still at 60 Hertz, right? And then the rotor speed initially cannot change instantly, so it is still at 900 RPM. Okay, so at that point slip was what, 0.1, right? Okay, and at that point slip is 1200 RPM minus 900 RPM divided by 1200 RPM, so it is 0.25. so slip actually increased. As the slip increased, the torque increased. Okay, it's already written here, torque is increased. So but your load torque is constant, so you have that excess torque in the red area. Okay, so in the red area or during that line, so you will have excess torque. So that means electrical torque is larger than load torque. So your system will increase until where? Until you have the next intersection point. So you can increase the frequency, the speed will stay at 900 RPM instantly, but at that point your slip increased, so you generate more torque, you draw more current, and your system will keep increasing its speed. The acceleration will reduce, but it will still keep accelerating until you reach your next operation point. Okay, so this is how you can increase the speed by changing frequency. So in the second example, we see the decreasing speed, and you have more options there. And in this case, let's say you were running at let's say initially again you were running at 900 RPM, and the synchronous speed, let's say it was 1000 RPM. Then you want to reduce to, I don't know, 750 RPM. Yes, you want to reduce to 750 RPM. Okay. So then, then you just drop your frequency. I don't want to calculate the numerical values, but let's say the synchronous speed of that one, I don't know, just to give an example, is 800 RPM. Okay, synchronous RPM. So suddenly you were running at 900 RPM when the synchronous speed is 1000 RPM. You were in the motoring range. So in that one, slip initially. This is for A, this is for B. So initially slip was 0.1, okay, NR is 900 RPM, and S is 1000 RPM. Then you just change the NS to 800 RPM, but your speed cannot change instantly. So it is still at 900 RPM, and I think if you calculate it, you can at least see your rotor now is rotating faster than the synchronous speed. So it is suddenly get into the generating mode, or you can calculate the slip and you can find it is negative, I think 125. Okay, so suddenly your torque, okay, you don't have to do the generating mode like that, but you jump from that point to that point, and suddenly your torque curve is still constant, and you have that extra, I mean not extra, but you are generating negative torque, and that area, actually in that case you will have TE is less than TL, so d omega over dt will be 0. So if you were running in motoring mode, you change the speed, you change the applied frequency of the motor. Okay, so you change the applied frequency of the motor, and your motor now gets into the generating mode, so it just reduces its speed. So first it reaches to 800 RPM. So from 900 RPM to 800 RPM, you are in the generating mode. Then you get into the motoring mode again, let's say 708 RPM, but you are not generating enough torque. You are not generating enough torque to compensate for the load torque. You are in the motoring mode, but the generated torque is not enough, so you still decelerate. So until when? Until you reaches that point. Okay, so applying a different frequency is kind of complex, but I hope you will see those things in your last experiments in the simulations. But those kind of techniques has really large advantages compared to external resistance connection or just changing the voltage magnitude, because by changing the voltage frequency, you will be able to actually sweep all the speed characteristics. And again, of just using the real actual torques is time consuming, and we use computer tools, simulations like Simulink or many others to calculate actual deceleration or acceleration curves. But if you want to make some assumptions, what we can do is we can approximate the torque, or we can simplify the torque as a linear equation. So this is the actual, if you remember, again, that was the equivalent I square. Okay, I'm dividing voltage by the equivalent resistance, then I am taking it square, so I have 3 V2N or V1 square, etc. Then this one is the power dissipated at R2 prime over S component, remember. So this is my torque expression. So as you can see, if the slip is really small, less than, and again at normal conditions, again here I'm kind of maybe exaggerated, but normally the slip is less than 10%, usually around 4 or 5% in induction machines. Okay, so if you think that one, so that one is divided by 0.05, it is like that one is multiplied by 20, so that term becomes larger than these two values. So for small values of slip, I can say R2 prime over S is much larger than those things. Okay, so if you just neglect those things and you have that component here, R2 prime over S squared, and then you have another R2 prime over S component, and once you write that one, it becomes S divided by R2 prime. So that equation is it's nice. So for, if you think that one as constant, again be aware if the voltage and the frequency is changing, that constant K will be different. But if you are working at small values, that equation tells the torque can be approximated as like with slip. Okay, so it is kind of linear, and actually you can see it maybe in the torque characteristics curve. Let me go back quite a lot. Okay, for example here you can see, yes, you have some fancy lines going out like that, but as you go to the synchronous speed, that one is kind of linear. So that means when slip is 0, you are generating 0 torque. If slip is 0.01, so you are generating some torque. If slip is 0.02, you are generating twice of that current, etc. Okay, so if you double the slip in that small operating range, torque will be doubled. Or similarly, you can get into the generating mode. Okay, let me go even back. So if you go to the negative range, so you will have the negative torque. So you can say in that range, okay, that curve can be approximated with a straight line as a function of the slip. Okay, so this is the slip range. Okay, so I will solve some numerical examples after that slide. So I hope you will find it useful. So by changing that one, okay, actually you can approximate how much torque I am producing when going from that point to that point. Okay, but please don't forget the speed cannot change instantly, so you cannot go from this point to this point. In order to go from this point to this point, first you need to go up, because your speed is still constant. You can change the frequency instantly, but the speed will stay constant. So now you are at that point, then it will keep accelerating. Okay, cool. So then, okay, we can change the voltage, we can change the frequency, but what happens if we change the frequency by keeping the voltage constant? So for in this case, if we reduce the frequency by keeping the voltage constant, again, I don't want to get into the details, but remember the equivalent circuit and the operation of induction machines is really similar to transformers. So I will give you an example, an equation that is familiar to you from the transformers. The induced voltage in the core of a transformer, and therefore in an electrical machine as well, can be represented as like 4.44, remember 2 pi over square root 2, times Fs, Ns, number of turns of that coil, times flux. Okay, or you can just remember that one is E is equal to n d phi over dt, and if this is in this sine version, sine omega t, once you take the derivative you will have another omega t omega term here, which we have the fs and also 2 pi f divided by square root 2. Anyway, so just remembering that equation, okay, if I keep the voltage constant and if I reduce the frequency, okay, I am applying more voltage but the frequency is less, so therefore the flux has to go up. Okay, so if I reduce the frequency by keeping the voltage constant, let's say at 230 volts phase voltage, but instead of applying 50 hertz, if I apply 10 hertz at 230 volts, then I will saturate the core. Okay, so saturating the core means you will not generate the torque that you require, and actually you will generate quite a lot of heat in the stator core, which is not desired. Or similarly, if I just increase the frequency with keeping the voltage constant, if I increase the frequency with keeping the voltage constant, then my flux again will get lower. So instead of running at an optimum, I don't know, 1.5 Tesla, maybe it will run at 0.5 Tesla. So, you know, having a, again, remember from the electromechanical energy conversion, you know, equations, if you have less B, then again that will reduce our torque and force magnitudes. Okay, so here actually you see an example while keeping the, for example, you apply some voltage at 20 hertz and then you keep increasing the frequency, but you don't change the voltage proportionally. So the voltage is constant, the frequency is changing. So at 20 hertz, I don't know how many pole, I think this is a 4-pole machine. Anyway, so at 20 hertz, so you have 600 RPM synchronous speed, so you have a torque curve like that. And then 30 hertz, so now your synchronous speed is at 900 RPM, so your maximum torque is around 250 RPM. So at 40 hertz, so the synchronous speed is 1200 RPM, but your maximum torque is reduced at that point. 50 hertz, at 60 hertz, at 70 hertz. So if you think as a control problem, yes, you can give, if I just draw here, so you can give any torque and speed characteristics in that area, but it will not be possible to drive a load that requires 200 Newton at, I don't know, around 1400 RPM. So that will not be possible. So I need to fix this. And the solution to that one is really simple. So I want to keep my flux in the machine constant. So in order to keep my flux constant, so that has to be constant. So that means if I am increasing the frequency, I need to apply larger voltage. If I am reducing the frequency, I need to reduce my voltage as well. Okay, so this is with constant voltage, and you can see the torque is reducing. And if I just, you know, apply, so increase, let me note here, increase F with voltage, so that V by F would be constant. Okay, so if you have constant V by F operation, if you just double the frequency, then double the voltage. If you halve the frequency, then halve the voltage. If you do, you know, that kind of operation, as you can see here, now the maximum torque can be kept at the rated value. Instead of spanning an area like that, I can now span an area like that. So I can find a combination of voltage and frequency to run any load at any speed. Okay, so that is really important. If my torque is like that, I can find the intersection point of that characteristics with that line, so I can find an ideal voltage and frequency combination to run the motor exactly at the desired operating conditions. Okay, so this is really commonly used in industry anymore. Like at 20 years ago, maybe the power electronics was expensive, but they are becoming more and more available. So now even the smallest industrial motors now have their motor drives. Okay, and those motor drives are called variable frequency drives, VFDs. Okay, you will hear that name a lot, VFDs, variable frequency drive. So again, this is a topic for your fourth year classes in the power electronic course, and also 462 utilization of electrical energy course. But the idea is, first I can, if it is a grid connected motor drive, what you do is you just convert the 50 Hertz to DC, then from DC to AC. Okay, so AC to DC converter here, then you will have a DC voltage there, then you will have PWM inverter, so that PWM inverter can generate any voltage and frequency. And actually, if you look at here at 20 Hertz, so it generates a small low frequency signal, and also its magnitude is lower, but it is generating that voltage with on and off voltage waves, PWM signals at a high frequency. And then if you want to go to 40 Hertz, then you will have a larger magnitude and a larger frequency, so you can see the PWM signals as well. Or at 60 Hertz, then you increase the voltage even more, and you can see how the PWM is changing. So you will have a speed command, and you have the PI controller. Then the PI controller actually calculates what should be the slip. Okay, what should be the required slip, and in order to give the required slip, what should be the applied frequency, and then in order to have the constant V by F operation, remember there's a linear relation as shown here, with the calculated frequency, what should be the required phase voltage to get constant flux operation. So once I know what should be the voltage and frequency of the applied signal, I can get control signals to my transistors. There are usually 6 of those things in a 3-phase voltage source inverter. So I can derive those 6 transistors to generate exactly the required voltage waveform. Okay. And again, here you see a detailed information. Again, this is outside the scope of this course, but if you are curious to get more information, please check those links. Okay, so this is how you generate from 50 Hertz AC to whatever frequency and voltage that you want. So in the constant V by F operation, so you can actually run your motor by changing the frequency, so you can run it like different slip values. So actually, depending on how you want to accelerate, you can move that point to the maximum. If this is T max point, okay, so you can adjust the operating slip to the here, that one as max T, so you can generate the maximum torque. Okay, and as the machine accelerates, you can move your frequency accordingly, so you will always keep the motor running at the maximum torque during acceleration. Okay, probably that generates more power than the rated operation. So that kind of operation can be tolerated a couple of minutes according to the design of the electrical motor, but you don't want to run this motor continuously at the maximum torque point. But that is the advantage of electrical machines. Although there's some rated power, rated torque, there's also some maximum power, maximum torque, which can give for short amounts of times. Okay, you can overload your machine for short amount of times, and actually that is what electric cars are using quite a lot. And by using that kind of maximum torque acceleration, you can really generate, if this is, I don't know, the difference between your load torque, you can generate quite a lot of positive net torque, which accelerate your system quite quickly. And the result can be seen here. The Tesla Rotor and Bugatti Siren machine. And actually, I think just last week Tesla introduced a Model S plate car, which is a 4-door family car, which over the maximum power is over 1,000 horsepower. Okay, so I'm not sure about the horsepowers of these two machines. Probably Bugatti should have the higher torque, but it cannot give that constant torque. So yes, there's a point where for induction machines, for internal combustion engines, to generate the maximum torque, but the Bugatti needs to change the gears. It will accelerate the motor. The revolutions for the internal combustion engine is different, and it will take some time to get to that at maximum torque point. But for Tesla Roadster, you have that kind of PWM controller. Okay, I want to go to that speed with the maximum torque available, so I can start turning my transistors precisely just to keep the motor at maximum torque during acceleration. So you can go from 0 to 100 kilometers per hour. It's less than 2 seconds. Okay, so I mean, you can see all those things here, and price wise, it is less than 1/10 of the price of a Bugatti. It's really expensive in Turkey, unfortunately, but you can get a really high performance. And please, again, I don't want to take your time longer, but please, watch a couple of these videos, especially Model S plate, which came out just last week. And again, it is similar in different electric cars. Okay, so you can see Porsche and Tesla Model S and Lucid Air Grand Touring, whatever. So they all have like really small accelerations, which you can get with supercars or racing cars. Accelerating from 0 to 100 kilometers per hour less than 2 seconds is quite impressive. And that power is, again, 1,100 horsepower. But the horsepower itself is not say anything. You can still beat the supercars, internal combustion engines with electric cars, because of that constant V/I of operation, that you can control the generating torque precise. But the disadvantage, not the disadvantage, but the limitation, voltage cannot be increased beyond the rated voltage. This may be sometimes limited by your battery voltage. You have, I don't know, exact value of the Tesla battery, but that DC voltage is limited. Or if you are driving some electrical motors connected to the grid, then you have some limited 400 volts line-to-line voltage. Or sometimes the coils, the insulation of the coils cannot go beyond some voltage. But if you want to keep the speed even further, then what is happening is you are getting into a rated voltage value. So you keep the rated voltage value, but you keep increasing the frequency. So as we discussed earlier, increasing frequency and keeping the voltage constant reduces your flux, and we call this region exactly the same thing. So this region is called, it's written here, we call that one field weakening region or flux weakening region. Okay, so therefore in this range, yes, you can give constant torque during acceleration. So for example, Tesla can accelerate, I don't know the exact values, but let's say it can accelerate with constant torques up to 150 km per hour. But let's say after 150 km per hour, then you reach your voltage limits. So you can still accelerate depending on your load line, but your acceleration will be smaller because you are getting into flux weakening range. And actually, if you have a look at that range, and again, let me write here, so power is equal to torque times omega, right? So at first region is called constant torque region as well, and the second region is called constant power region. So if you are at constant torque region, this is base, this is rated speed, let's say. Okay, and let's say this is V rated, this is say P rated. Okay, so at first you start with, blue is the torque, you start with constant torque, so torque is constant, okay, and you increase the speed. So as you increase the speed, torque is constant, power will be increased, so your motor is drawing more and more power. Okay, and similarly it is at first for constant V by F. So F is proportional with V, and frequency, applied frequency is proportional with the synchronous speed or rotor speed. So I can say during constant torque region, the applied voltage, which is that line, is also increasing until you reach that point. They don't have to be exactly the same point, but anyway, it's shown like that there. So once you reach at that point, you don't want to apply larger voltage than your rated voltage, or as I said, maybe you are limited by the voltage limit of the battery or grid voltage, etc. So you can keep the voltage constant, but if you keep the voltage constant, then your torque, because your flux was constant, the green was flux, the flux was constant during that region, but after that flux will be reducing. As the flux reduces, the maximum torque that you can generate also reduces. As the torque, in the second region, I still have that relation. So speed increases, but torque reduces. So power is kept at the constant kind of range. So the second range is called constant power region. Okay, so your deceleration can get, your acceleration can get smaller, but you can still manage to accelerate your motor or your electric car, whatever. So there are basically two regions in induction machines, and most of the time if you are running at constant torque region, you can control by using a variable frequency drive, you can control it really quickly. And the maximum, how far it can go through here, depends for a couple of factors. Again, for what is the voltage level that you can apply, what is the magnetic flux value in your motor, or the phase currents. Similarly, cooling, yes, running at higher currents will generate more heat in the electrical machine, so you need to dissipate that somehow. And in some cases, you can run the motor quite a higher speeds. I think for what was it? I think for Model S plate, it was running over 20,000 RPMs. Okay, so technically it can even go higher values than that, but there can be mechanical constraints. You can have some limitations in the bearings that you use, the centrifugal forces. Once you are running at 20,000 RPM and gets really high. So in the Model S plate, I think they use some kind of carbon fiber sleeve just to keep the centrifugal forces constraint, just to keep the rotor in place. So you can have that kind of mechanical limitations as well to determine the maximum speed that you can achieve with the motor. Okay, so thank you.